Yeah, it's your boy Chili here. Welcome back to D3D 12 Shallow Dive. Last video, we set up our project. Everything is ready to go. Let's get coding. In this video, my main goal is I just want to be able to clear the back buffer and present it so we can, get some kind of a color onto the screen. Just gonna do a little reorganization here. Move these headers that have to do with like DirectX, Direct3D. We'll put them in their own little section here. Now we gotta include DXGI, and we should include D3DX into here. All right, so what are we gonna do? Well, we've already kind of started. Well, no, this one is not what we do first. The first thing we really wanna do is we wanna get a DXGI factory. That's the thing that you use to create your swap chains, among other things. Let's just put some constants in here. The width and the height of our screen buffer count. Note that in general you can't have less than 2 buffers, so we're running with the minimum here. Let's create that DXGI factory. And there's lots of versions of this. We're going to go with number 4, and we want to create a debug factory that's going to get us extra debug information. You might be familiar with that if you've seen my Direct3D 11 video, but you get a lot more information out than you just get with the H results. You get barely anything with those. So we'll create our debug factory, we get our debug information, and then it's time to create the device, the Direct3D 12 create device. A more rigorous approach would be to use DXGI to then enumerate all the adapters and choose a specific one to create the device on. But we're just going to take the default one. We want to keep the code simple here. Right, the next thing we got to create is a command queue. This is a very important thing in D3D 12. In 11, you would have just an immediate context you could send rendering commands to, and then the driver would figure out all the scheduling and everything. But now you've got to package up all your commands into command lists and then submit those lists to a command queue. So there's a diagram from Microsoft. So you have different threads. They're submitting command lists to these command queues, and then the GPU, pulls things off the command queue and executes them. First in, first out queue. Not super complicated. Like many construction functions, we create a descriptor and we set up, parameters for creating the command queue, and then we call create command queue and we get one of those bad boys out. There's different types of command queues. Direct is a 3D command queue. There's a command queue for compute, and there's a command queue for copy. You can have multiple command queues and give some higher priority and some lower priority. That's pretty advanced usage. We're just going to create a default 3D command queue to do rendering with. By the way, it's interesting to note that 3D queue can basically do everything. A compute queue can do compute and copy, and a copy queue can only do copy. And there's reasons for that, but we won't worry about that. The main takeaway is that if we have a 3D queue, a direct queue, we can do anything we want, and that's great. Now we create the swap chain. It contains the buffers that are going to be used to render to, your render targets, and it's tied to a window. And this should be super familiar to you from D3D 11, because it's DXGI. It's not tied to any specific D3D API. It's common to all of them. So it's the same stuff. You give the width, the height, the format, sampling, all that crazy stuff, and then you create swap chain for window handle. So this is where we're going to need our window that was passed in here, get the handle for that, pass in with the descriptor, and create that swap chain. And this function gives you a swap chain version 1, and then we can just upgrade that to a swap chain version 4. Another little interesting thing to note here is that swap chains, they have a connection to a command queue. So there's a little bit of a connection there, and that's does a little bit of synchronization behind the scene with regards to present operations. So most of the synchronization in D3D that you do it yourself explicitly. But here's a little implicit synchronization that's being handled under the sheets for you. A little rare for D3D 12. Actually, what I think I'm going to do is I'm going to not set this flag here, the allow tearing flag. It requires support in hardware, so we should really check for it. And I don't really want it right now anyways, but it's very important if you want to support variable refresh rate monitors. But we won't worry about that. We'll just set that 0 right now. Let's move on. Next thing we're going to create is something called a descriptor heap. So RTV should be familiar to to you. It stands for render target view. The idea is in Direct3D 11 already. You have resources, and then you have views on the resources which tell, the GPU how to interpret the bytes in the memory of that resource. And in Direct3D, you would just create these views, and you would get, COM objects for each one of these views. Now in 12, you don't get like a COM object that's wrapped up for you that represents the view. You have to create like a heap, a section of memory, and you write the views, the descriptors into that memory, and then you do like pointer stuff, and you got to manage it all yourself. So there's no nice COM ref counting or anything on that stuff. It's all on your plate now. You handle everything. So the heap itself, you get, a COM pointer to reference that. You create the heap, and then every individual descriptor in there, you manage it yourself however you like. So our descriptor heap has a type in here, and this is a type render target view descriptor heap, so it can only hold RTVs. We need one descriptor per buffer in our thing, which we have 2 buffers, so 2 descriptors. Now, in order to index in our descriptor heap to get, the first buffer, the second buffer, we need to know the size of an individual descriptor in there, which depends on the hardware, right? Different hardware will have different implementations, different sizes of their descriptors. So we have to call this function to get the increment size so we know how to move around within that heap to index into it. All right, so now that we have our descriptor heap, we can create the individual descriptors for each of those buffers. We're also going to cache some references to each of the buffers so that we can use them, when we're selecting the new one to draw to. So since we have to iterate over the buffers to create the descriptors for each one and cache them, we do those together in a single block of code here. So an array here of COM pointers to hold references to the back buffers that are, embedded in the swap chain. Here we see the first introduction of using these D3D X types. This one is a descriptor handle, which you can think of as just basically a pointer into a descriptor heap that points to a specific descriptor. So we create one, we initialize it to the beginning of the heap. We're going to loop over the number of buffers that we have. And for each one, we're going to call getBuffer on our swap chain. And I'll store a reference to the buffer in our array here. And then for that one, we are going to create a render target view. And then we call offset by our render target view size, which offsets to the next render target view in the descriptor heap. Now we're going to create the stuff that you need to actually make and dispatch command lists. So you need 2 things. You need a command list object, and you need a command allocator, which is kind of like the memory that backs the command list object. And creating the command allocator, there's nothing simpler than this. It should be a direct type because this is going to be used with direct command lists to, submit 3D rendering commands. So you create the command allocator, then the command list. Create command list has more parameters than create command allocator, but this one's obvious, right? Types match up. This one's obvious. That's the pointer that you're going to set. Also, when you create the command list, you've got to give it a command allocator initially that is backing that command list. I don't know if you have to. Yeah, it seems like you have to. It's not optional. But it can be targeted to different command allocators later on. It's not tied to that one for its whole lifetime, by the way. Node mask's not that important. If you have multiple adapters, that becomes into play. And you can also give it an initial state to work with, but we're not going to do that. Now, one thing that we do here is we close the command list right after we create it. And that's just because the beginning of our rendering loop is going to expect the command list to be in a closed state already. So we're just going to set it up so that it lines up with the beginning of our loop, basically. All right, now we get to the very interesting stuff in Direct3D 12. In the very beginning of when working with it, this is the kind of stuff that might take a little bit to wrap your head around. The synchronization. You have to manually synchronize a lot between the GPU and the CPU. And the way you achieve that primarily is with something called a fence. All right, let's do a shallow diagram crash course in fences in Direct3D. So you got a CPU, it's building up command lists, submitting them to the command queue. So you got your command lists in here. Now, each of those lists, those command lists, they haven't been executed yet by the GPU. They're waiting. They reference a bunch of resources, right? They want to draw to like something in the swap chain. So they probably reference like a render target. It might not be in swap chain. The command list is stored in memory that's backed by a command list allocator, etc., etc. It's referencing resources. So as long as those commands are in flight, you can't like destroy or reset any of these resources because you'll invalidate the list. When the GPU now tries to execute the list, it's going to screw everything up. But you want to often reuse many of these resources. So how do you know when it's safe to reuse the resources? What you do is just as the same as you insert, I messed up my diagram a little bit. We're basically inserting in the back. So this is the newest thing. This is the oldest thing. This is what's going to go to the GPU. Anyways, so what you do is after you insert your command list, you put a fence in there and you give it a value. That's the signal value of the fence. And then what you do is you can check that value. You can check the value 69 and by asking, the device, what is the signal value on this fence? And when it comes back as 69 was signaled, you know that this has been executed and this has been executed and all these things are now free. So you insert a signal into the queue, and when the queue actually reaches that point, when everything in front of it has been executed, then you'll know. And you can check that value for the CPU, and you can also wait on the value. So you can sleep and wait for this value, and then your thread will be woken up as soon as this has been signaled. And just a general rule of thumb, you keep these values, increasing. You don't reuse fence values because that'll make confusing things happen. You just say every time you insert a new fence, you just give it an incremented value. So that being said, creating a fence is very simple. You got a handle to the fence, give it an initial value that we're going to store on the CPU side. We're going to keep track of, what value is in the fence. And then we just create our fence default, no special flags or anything. Now we have our fence. Now, I told you for the CPU, you can wait on a fence and you create a Windows event object to do that. And that's just done with the standard Windows create event function. We get a handle to our event. And that's it. That's all the setup that we need to do for this. It's actually not too bad when you're not, actually doing any rendering, but still a lot more than in Direct3D 11. Now we hit the render loop. So we're going to keep track of what the current back buffer that we're working with is, and we are going to loop while the window isn't closing. In fact, better than just assuming which one is the current one, assuming 0, we can call get current back buffer index to set this up. That's even a little better. All right, so the first thing we want to do then is, select the current back buffer to render to. Just get a reference into our cached array of resources, pointers to the back buffers. Now, we have to set up our command list to get it ready to record commands to. So we reset our command allocator and we reset our command list and give it the command allocator used to back it. So here you can see every time you reset the command list, you can give it a different command allocator. It doesn't have to use the same one every time. So now those are all ready to record to. And so now we want to clear our render target. All right, so here comes a huge difference between Direct3D 11 and Direct3D 12. Resource barriers. These things did not exist before. And basically, when you're doing an operation on some resource, it has to be in a certain state in order to do that operation. And when you want to do a different operation, it's going to need to be in a different state. And so you have to create the transition between those states. And you have to manage, basically, you have to know what was the state it was previously in and what is the state that you want it to go to now. So before, this stuff sort of thing was like the job of the driver to figure out. And it can be very difficult for the driver to figure it out from an application that's trying to do these things in a multi-threaded environment. And it wasn't able to do it very efficiently. And that's one of the reasons why Direct3D 11 wasn't really good for multi-threaded rendering. Now you have the responsibility to do this, and if you do it correctly and efficiently, you can get great gains, but it's not easy. Now, the reason why barriers are required in the first place is kind of complex, and that's not really a topic for this shallow dive. But, for example, a simple example would be GPU's cache texture data, right? So if it's been doing a bunch of reads, it might have a bunch of texture data in the caches. And if you want to write to that texture, you've got to transition, you got to give it a resource barrier transition, and that will tell it, okay, he's now going to be writing to this. I got to flush my caches, otherwise I'll be reading stale data. The barrier tells it what it needs to do. If you insert barriers where they're not needed, the GPU does extra work and it's not efficient. It's up to you to track and to figure out when they're needed and when you don't need to put them in there. Now, in our situation here, we are transitioning the back buffer, and we're transitioning it from a state where it's able to be presented to a state where we are able to render to it. So we transition it into a render target state so that we can do a drawing operation, the clear, right? We use the D3D X12 resource barrier class that has a nice transition function in here that can create the barrier based on the resource and the starting state and the ending state, and then we insert our resource barrier. You can insert multiple at once, batch them together, which is often efficient, but we're not going to worry about anything like that right now. Once we have transitioned, we are able to clear the buffer. All right, so now we clear the buffer. We got to create a color, which is just an array of floats, a nice blue color here. Create a handle to the RTV descriptor by getting the start of the descriptor heap, indexing into it by the current buffer index using the size of a single descriptor. And then on the command list, we issue a command to clear the render target view. So you can see here in our command list, we got two commands. One to transition a resource from one state into another, then a command to act on the resource. Now finally, you might have predicted this one, but now we transition, we're into the render target state, but we want to present this, right? We finished clearing it. We now want to put that onto the screen. So we've got to transition back into the present state. So that's another barrier. All right, now that we finished writing to our command list, let's submit it to the queue. First, you have to close a command list, and then you submit. You can, submit multiple command lists together. So we create this array, just has one in it, and then we submit that. Now, just like I got in this diagram here, after we submit our command list, we want to put a fence in there so that we can get information about when it has completed. Why? Because we only have one command list, and more to the point, we only have one command allocator. So we have to know when the command list has finished executing, because that's when we can reuse our allocator. So after we call execute command lists on the command queue, we do signal. We signal our fence onto the command queue using the value that's just, a local variable that we have here. And we increment that value, so we're going to get a new one every time. Then we call present on our swap chain. That's the same as it was in Direct3D 11. And then we are going to wait for the command list and the allocator to become free. Now, technically the command list, you can reuse it as soon as you have submitted it to the command queue. So once you've finished, you closed it, you submit it, you can reuse it right away. But the command allocator cannot be reused until all the commands have finished executing. So what we do is we have our event object. We use our fence object, which is a D3D12 fence interface, set an event on completion. So the last fence value we set, because we incremented it, the last value is the current value minus 1. And we say get an event that will fire when this is actually signaled, meaning when the GPU works through the command queue and gets to our fence. So we set that event, and then we wait on that event. We're going to have no timeout. We're going to wait until that event is signaled, and that'll block here. Our thread will go to sleep until a previous list was done and we are able to reuse our stuff. Now, just a side note here, it's probably pretty obvious, but this is not generally how you want to do things, because in this mode here, we have to wait for the GPU to finish before the CPU can do more work. So it's always, there's no parallelism between the CPU and GPU. One is always waiting for the other one. But for our simple example, this is fine. And now we advance the back buffer index to get to the next one. We are ready to go back up to the top and do it all over again. Although now that I think about it, this is probably not that necessary. All we could do instead, we could just do that operation at the top here and then just don't initialize this one outside of the loop. That's fine. This will work. Okay, cool. So now we have our render loop. So let's build it, see if we got any problems in there, and then maybe give it a run. Well, we definitely have problems. All right, so it's all freaking out on this D3DX header stuff, and it just says like this D3D format layout is undefined. I don't know what I need to get this working here, but I mean, I have the old one that's just a single header, and it works fine, so I'm just going to put that one in here. So let's just delete all this. We'll worry about it if we decide we actually need the new one later on. So I'll just copy the single D3DX header. You can see it's a chunky boy, 200 kilobytes. All right, let's try to build now. Okay, so static analysis is a little annoyed. There's something uninitialized in there, but that's not a problem for us. Let's see if we get our light blue, and we do. We do get our light blue color. Looking at my console here, I'm not seeing any errors. And if I close this, pretty clean. Don't see any huge issues in here. So there you go. We have our first initialization, and we are able to clear the back buffer. In the next video, we are going to investigate this code a little bit. We're going to find some problems with it and fix them. And we're also going to make it a little more interesting by cycling the color. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more Shallow Dive.